All right, this is all about orthogonality. So one thing that we need to make sure that we know about orthogonal sets is that every single, let's maybe call it ui times uj, inner product must be equal to 0 if we have an orthogonal set. So let's look at this example, and we need to consider all different pairs. So we need to do u1 dot u2, so 3, 1, 1, with -1, 2, 1, and I get -3 plus 2 plus 1, and that's 0. I need to do u1 with u3. Okay, I need to write this one out. -3 halves minus 2, and then plus 7 halves. So that's 4 halves here. Yep, that's 0. And then u2 inner product with u3. And so we get 1/2 minus 4 plus 7 halves. 4 it would be 8 halves, and so I get 0. So that's how we show that a set of vectors is orthogonal, is all of the inner products end up being 0. Our second example to go through on this topic is to show, so we say that this is an orthogonal basis. We have 3 linearly independent vectors in R3, and we want to express that vector as a linear combination of the combination of vectors in S, okay, where S is that set. So if Y is a linear combination, then that means that Y must be equal to C1 U1 plus C2 U2 plus C3 U3, right? It's a linear combination of those pieces. And so how do we find those C1, C2, C3s? Well, there's a theorem in our book that says that Cj is equal to vector y times uj over the inner product of those. So if I want to figure out what C1 is, I need to take y I need to multiply it by u1. What was u1 up here at the top? Or dot product with it, sorry. 3, 1, 1. And then I need to divide that by the dot product of 3, 1, 1 and 3, 1, 1. All right, so we get 18 plus 1 minus 8 on the top. So that gives me 11. And then I get 9 plus 1 plus 1, so I get 11 on the bottom. So I get 1 for C1. So it's 1 times U1. And then I would do that for each and every vector here to figure out what the C2 and the C3 is. When you do this, you end up getting C2 is -2. And you end up getting that C3 is also -2. And so y must be u1 minus 2u2 minus 2u3.